Okay, good morning. So, this is one of the most important lessons that you will probably learn in Math 3C, and that's the notion of integrals. So I will go through a lot of material probably today, as much as time will let us. But you might be some of them are. It seems quite hard or something. The concept is not hard, but might be the calculation. I want you to see this calculation once. It's a lengthy calculation. I want you to see that in order to appreciate what will come later. Not because I want to. That's up to you, of course, if you want to learn it or leave it. But I think it's really instructive if you see how people could do these calculations before Newton and after Newton. Okay, so you want to understand that a little bit. So then I would think that you will appreciate it if you see the calculation in its own length and try to understand what are the obstacles in front of those kinds of calculations. But at least the motivation of talking about integrals is very simple. I don't know, even from ancient times you are interested to measure the areas of lands probably, and usually lands are not limited with the straight lines unless you draw the borders with hand. Usually the lands are curved and things like that, so the border of the lands are curved. So if you want to calculate the area of shapes so that are limited to straight segments, probably it's not hard, because what you need to know is to know the area of a triangle, and then you partition your shape into different triangles, and then if you can calculate the area of each and then add them up, you will get the area of the total object. Yes. For example, if I ask you to find this 1, 2, 3, 4, 1, 2, 3, 4, 5. That's a pentagon. Yes. So if I ask if you have a piece of land in this form, and I ask you have some measuring instruments in your hand, and you're supposed to find the area of this pentagon. So then what you do, for example, you can just draw this line and draw that line, and then find the area. It's possible, because, for example, here you can measure this length, you can measure the height, and multiply, divide by 2, you'll get the area of this one. The same for this one, the same for that one, and then add them up. Okay, now the question is that what will happen, how can I understand the area if one of these are curved? Of course, you have already answered this question for one particular case, and that's the case of the circle. Yes, even for the circle, you have already used the formula pi r squared for the area, but I don't know how many of you have seen why this is true indeed. So why the area of a circle is what it is, yes? Okay, so, or the area of an ellipse or something like that. So that is the point, is that people want to, mathematicians, they want to be able to answer this question, finding the areas of shapes which are not limited to just only straight lines, but sometimes curved lines, yes? And when you are a mathematician, your desire is, I don't know, this is the natural tendency that you want to solve it as general as possible. Even this curve does not appear in nature, they doesn't care, for example. They want to be able to solve it in the most general context. But let us try to start a motivating example and then going forward. So I want to exaggerate a little bit about this graph. So let me start with a very simple graph. Y equals to x squared. And then I consider it on the interval between 0 and 1. Okay, so if I want to draw the picture for you, and then I will try to exaggerate a little bit to make it a little bigger so that you can visualize. And at some point it would be a good idea if we go to GeoGebra, but I want you to understand what is happening so that when we go to GeoGebra, you appreciate it. Okay, so y equals to x squared is this curve. It's a famous parabola. But on the left-hand side, I don't care, so I don't draw it. I want to concentrate only from 0 to 1. Of course, let me take this one 1. If I put 1 to this function, y also becomes 1. So if this is 1, and 1 should be here, but I rescale it in a way that I can fit it in the whiteboard. So I will take this one to be 1 here as well, okay? the scales on the x-axis and the y-axis are different because I want to facilitate my job here. So, and then I know that if I give 0 to this, it is 0, and then you know that also here, this is the point 1 and 1. So my parabola is coming from this side somewhere, which I don't care of this part, and then it will go up to here, and it will continue, yes. My goal is to somehow to understand how can I calculate this area. It's not a triangle, of course, because this one is not a straight line, it's a curved line. This is a straight line, that's a straight line. But I am interested in finding this area which is limited between these two lines and this curve. Yes?
Can you also do for the other shape?
Yeah, we can always do so, but I'm just motivating. That's a motivating example. I want to start to see the idea. The ideas that I want to introduce here, you can actually extend to other functions as well, or in different parts. Of course, if I can calculate this area, this is just a rectangle. I can subtract this area, and I will get this one. That's it. But for the time being, I want you to understand. I want to be able to calculate this area. Yes? So what we want to do is to start approximating this area rather than calculating it exactly in the first place. So the first crazy idea is to calculate the area of this rectangle. What is the area of the rectangle, by the way?
1.
1. And say that, okay, the area of this one is also 1. But of course, this is an approximation. It's better to say 1 rather than 100. So 1 is not a very good approximation for the area. This part is your error. If you say the area of interest is 1, then you have made a very, very big error. Yes? Yes.
Can we say that? Can we pretend that it is a triangle, and then we can do?
No, that's a difference. That is the way. Actually, by the way, Archimedes was able to solve and find the exact value, and he did it based on triangles. But then in modern mathematics, we do it based on rectangles rather than triangles. And the answer he got is the exact value. Yes. Yeah. So, and then this is really, so he was really a genius. So because I will tell you, if I don't remember exactly what he did, but he found a very, very interesting way to calculate an infinite sum. Even the notion of infinity was not that much understood at that time, because what is infinity, let alone I want to sum infinitely many numbers. Then you will see that we will come up to an infinite sum, and he was able to design a geometric way to understand what will be the limit of that sum if we continue with infinitely many terms. Okay, so one possibility is to say that, okay, the area that you want is 1 times 1. Okay, but let me just put approximation. What I want you to write is this. This one is this height, and that one is this length. Yes? But there is another way to write this 1. How did I got this as 1? For example, if it was 2, what was this height?
2.
No, if it was 2, what was this height?
Say 1?
No? It would be 4, come on.
But
You
the-
put
the
2
height
here,
is like
you get
1.
4.
Oh,
Okay.
Yes?
That-
So if that was 2, the height should be 4. Yes? So how did I get the function? How did I get it? So I would say that this f, this 1, is f of 1 times 1. Yes? So what is f of, this is f of x. So this, you see that this length is actually the value of the function calculated at this number. If this number was 2, then this height would be f of 2, which becomes 4, yes? But here, as for simplicity, what I want you to understand, another way of writing it 1 times 1 is to write f of 1 times 1. Yes? Okay, now, let us do it in this way. Let us just divide this interval into 2 equal pieces. And then this becomes 1/2. And what I do, I draw a vertical line from here so that it will intersect the curve. And I will draw a vertical line here so that it intersects the curve. And then what I do, I complete two rectangles here. One here. So this is my rectangle. And another rectangle here. Yes? So what I have done now, I have partitioned my interval to two equal segments. And then from the midpoint, I drew actually a vertical line. And whenever it intersects that one, I completed this rectangle. And I did the same thing here. I completed this rectangle. Then what I have done, now what I have two rectangles. If I say the area of this rectangle plus the area of that rectangle is what you want, it's not still true. Yes? So, but let me just write, but at least I want you to understand this process. A is approximately still equal to the sum of this area plus the sum of that area. Yes? But how much is my error? This shouldn't be calculated, but I am considering it. This shouldn't be calculated, but I am considering it. Okay? The sum of these two red parts is my error. But what was my error before? The error before was that part. Yes? So what I am doing, by dividing it into two parts, I reduce the error. I make the error less. Still, this and that on top of each other gives me the error, but I hope that you agree with me that this plus that one is the new error. The previous error was that big. So at least I throw this part away. So this means that if I add the areas of these two rectangles, it is not still the exact value, but it is better than before. But that's the whole idea. So now can you tell me how should I write it? So the area of this is what? 1/2 times which number? Can you tell me now? The area of this rectangle is what? This width times this height.
1/4?
1/4, yes? Plus this width, which is still 1/2, but times 1. But if I want to write it in the language, so let me keep everything as before. I want to be careful here. So f's should be on the right. So let me write it like this. I will start multiplying the height first. As you said, 1/4 multiplied by 1/2 plus 1 multiplied by 1/2. Agree or not? But what is f of 1/4 is f of 1/2 multiplied by 1/2 plus what is 1? F of 1 multiplied by 1/2. I want to put it in the form of a pattern as well so that we can guess what's happening. So this is just a very simple calculation. I am adding the areas of those two rectangles. But then I wrote it in a different way. Instead of 1/4, I write f of 1/2, which is exactly 1/4. And instead of 1, I wrote f of 1, which is exactly 1. Understandable? Yes? Okay, now, what happens, the point is that the error becomes less. And the idea is that if I continue this partitioning to more and more rectangles, what happens, I will have more rectangles involved, but the total error that I will make in the new partition will be less and less each time. That is the whole point. I want you to understand that. So that was actually the observation Archimedes made with just making triangles. Okay, so for example, 1/3 is not a good point to calculate, but let me make it a little bit. So let me make it to 4 ones. So I divide this one to 2 rectangles. I divide this to 2 rectangles. So because if I want to make it a third, in principle you can make it a third, but let me just make it 1/4 here. And then what will be this number? Can you tell me?
3/4.
3/4, yes. Okay, so but the picture might be a little bit messy, but this is the last one that I want to do. Okay, what I'm supposed to do? How many points I have? 1, 2, 3, and 4. So I have 4 rectangles to construct right now. What I do, I will draw a vertical line. Whenever it touches this, I make a rectangle out of it. Yes? And then I do the same thing. I will get this rectangle this time. I do the same thing here. I will have this rectangle. And I will do this one, and I will get this rectangle. Yes? So now I have 4 rectangles, but what are my errors? You see, this is one part of the error that I am making. Yes? Another part of the error is exactly this one. Another part of the error that I am making is this one. Another part of the error is this one. Do you understand what I mean by error? These are supposed not to be counted, but I am counting them. But I hope that you see that the sum of the orange parts is smaller than the red parts. So it means that I am making the error even smaller. Is that understandable? Okay. So then it means that still I cannot claim that A is equal to the sum of these because I am making some errors again. But first of all, let me write the formula. Can you write the formula for me? The area of the first rectangle is how much? What is the height? Can you tell me this is small height?
1/16.
1/16. Multiplied by what?
1/4.
1/4. Then I go to the next rectangle. So what is the height? 1/4. So you are putting that number into the function. What is the width or length? Is again 1/4. And I go to the next rectangle. Can you tell me what is the height? What is the height of this rectangle?
9/16.
9/16, exactly. Multiplied by 1/4 again. And finally, what is the height of the next one is 1 multiplied by 1/4. Yes? But if I ask you to write it as before, instead of 1/16, you can write 1/f of 1/4 times 1/4 plus f of 1/2 times 1/4 plus f of 3/4 times 1/4 plus f of 1 times 1/4. Okay, and if you want, we can also do some calculations, by the way. The rough approximation, the area is 1 by this approximation, which is actually a very crude approximation. But the next one is better, so can we do it in our head? So this is 1/2, this is 5/8. Yes? Yes. And then here, by the way, you see 1/4, 1/4, 1/4, 1/4 is in common, so I can pull it out. And then what I have I have to add it. 1/16 plus 1/4 plus 9/16 plus 1. So I can write it as 4/16. I can write it as 16/16. So it is 10, 14, 30/60. So if I simplify it by 2, it becomes 30/16. If I simplify it by 2 is 8. And then I multiply it. So it's 15/32.
Ustad,
Yes?
do you say 1/4 plus 1/2 plus 1/2 in the first one, or?
What?
Never mind. I think I'm making a mistake.
No, you multiply these
Multiply it.
two. You
Okay,
multiply
yeah.
these two and then add them.
Okay.
It becomes 5/8.
Yeah.
And then this is the way that I calculate, but you don't need to bother. You just multiply these two, multiply these two, multiply, and then add the results. If I haven't done something wrong, hopefully, the answer that you will get is 15 over 32. Okay? So we can actually continue. But if I have done something wrong, it means this 1 is an approximate value for the area of interest, but it's a very bad approximation. This is still an approximation, but a better approximation. That's a better approximation, a better approximation. But now look, if you really want to do it, if you want to get the exact value, what do you suggest to do? Because assume that I continue this with more rectangles. For example, let us make it 10 rectangles. What happens? I will not be able to get rid of the errors, yes? The point is that the errors that I am making become smaller and smaller. Yes?
So we could say it goes on infinitely
Infinitely, yes?
I'm confused. What you wrote 15 over 32, and then you wrote 15 over 8.
Forget about those things. Calculate this number. It should be 15 over 32.
Okay.
Okay. It might be wrong. We can check it with GeoGebra later. But what I'm saying is that this number, if you calculate, is this one. Might be I have done some mistakes, so we will see that. But the point is that is a problem. So I hope that you agree. If I make it 100 rectangles, the error is small, but there is an error.
Yeah.
If I make it 1,000, there is an error, small. 1 million, there is an error, but small. So in principle, it means that we have to do it infinitely many times. But there is a very small practical problem when it comes to infinities. We cannot reach that limit. Okay? So even if you do it billions of billions of billions of times, it is not still infinity. Okay? So that's why when you work with infinities, but at least intuitively something becomes clear. If I can do it infinitely many times in some way, then if I end up with a number, that number is a reasonable number to say it's the area. Is that understandable? So that process I want you to understand. Okay? That's it. But now I want you to also write this in a little bit formalized way. Okay? So what we say is that I intentionally wrote them with F, but I want to see that what happens. So can you see, in the first case, this number that appears was 1 everywhere. In the second case, it was 1 over 2 everywhere. In the third case, it is 1 over 4 everywhere. Yes? So now, assume that so here I divided my interval into 1 rectangle. Here I divided into 2 rectangles. Here I divided into 4 rectangles. So if I divide it into n rectangles, one is clear. So this A is approximately equal to. So what happens what will play the role of this 1, 1/2, 1/4 if I have divided my interval into n equal pieces? Yes?
1 over n.
1 over n, yes? So because the whole length is from here to here 1 unit, if I divide it into 2 parts, each part becomes 1/2. If I divide it to 4 parts, each part becomes 1/4. If I divide it to n parts, each part becomes 1 over n. Okay. Another thing that I want you to tell me is that what should I write for f? So you see, what are the numbers appearing here? In that case, it was 1, f of 1. In that case, it was f of 1/2 and f of 1. In that case, it is f of 1/4, 1 over 2, 3 over 2, and 1. Okay, can you tell me what happens? So let me just do it like this. Let me just draw another picture for you. So assume that you have this scenario. Here is 1, and you divide it into n equal pieces. The first part is 1 over n. Do you agree? What is the second part? 2 over n. So what is the third part? 3 over n. And then it will continue. So what is the first interval? The first interval is between 0 over n and 1 over n, because another name of 0 is 0 over n. Yes? So the first interval is between 0 over n and 1 over n. The second interval is between 1 over n and 2 over n. The third interval is between 2 over n and 3 over n. And another way is that, what is 1, by the way, if you want to, n over n. That's the last one. So what is the previous one? Can you tell me? So 1 over n, 2 over n, 3 over n. You continue this until you reach to 1. But another name for 1 is n over n. So can you tell me what is the exact point, what is the point previously, exactly before this? Yes?
N minus 1 over n?
N minus 1. So is that understandable? So if I divide from 0 to n equal pieces, these are the numbers that I have to work with. 1 over n, 2 over n, 3 over n, etc. Okay, now for the first one, I complete this square. It's very small, I hope that you can see that. So the first one, I complete this square. The width is 1 over n. I have written it here. But can you tell me what is the height here? Let me make it bigger for you. So here is 0. Here is 1 over n. I am asking you about this height. What is this height?
F over 1 over n.
F of 1 over n. Yes? Can I go to the next one? Can you write a formula for the next one? The next rectangle. So let me just draw it again here for you. Now my situation is here. Here is 1 over n. Here is 2 over n. And this is my situation. Okay? And I want to complete this square. This rectangle. So what is the width? What is the width?
1 over n.
1 over n again. But what is the height? The height is? F of 2 over n. Understandable or not? Yes? Is that clear? So the next rectangle is here. The height is f of 2 over n. The next rectangle is here. The height is f of 3 over n, as before. So this means that I have to continue this sum until I reach to the end, to the final one. N minus 1 over n times 1 over n, and plus f of n over n times 1 over n. I intentionally wrote n over n, but of course n over n is just 1. Yes? Is that clear? Okay, but this is still approximation. But I write it in the form of a sigma. Okay, so can you write it as a sigma? So this becomes sigma. Do you know sigma? Yes. For example, if I see sigma a k, and I say k goes from 1 to 5, what do I mean? I mean replace k with 1, replace k with 2, until you reach to the last one, and then add them up. That's the meaning of sigma, yes.
But integrals have like a special notation, right?
Yes, I will come to that. Okay, so a is this one. It's a sigma, yes? So can you write it in a sigma? You see, 1 over n is common, so I put 1 over n again. I have f here, and the denominator is n, 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 n. Everywhere n. So the denominator is n. But the numerator in the first one is 1. In the second one is 2. In the third one is 3. In the last one is n. So I write k over n, but I run k from 1 up to n. Yes? So what I have done nothing except use a very common symbol in mathematics to write a long sum in a compact form. If you are not very happy with this one, you can imagine it in that way, but I want you to learn. When I write a sigma, k goes from 1 to n, it means replace k with the first number, replace k with the second number, and do it until you reach to the last number. You get a lot of terms, add them up. That's the meaning of sigma. So that's an approximation, yes? But now, intuitively, we realize that if I want to take this away and put equality sign, what I am supposed to do? Yes?
And needs to be infinity.
Yes. And you have learned a little bit about that. This means the limit of that sum yes? And when n goes to infinity. Because no matter if I do it 1 billion rectangles, still it's approximation. Apparently, I can get rid of the errors only in one scenario, and that scenario that n is infinitely large. But of course, there are practical problems because what is the meaning of infinity? But at least we know how to calculate limits. Yes. So the only thing that I want you to understand. I really don't. That's up to you. If you are interested in mathematics, just learn them. But what I want you to, the goal of all this discussion is to make this formula plausible for the area. Yes. Yes.
Why didn't you make the first one approximately and then when you wrote into the figure you blank?
No, because if I approximate, it means that n is a number, 10, 1,000, 1 billion. It doesn't matter how many partition I do, still I get error. But the point is that when I increase the number of rectangles, the error are getting smaller and smaller. But they will never be zero unless I do it infinitely many times. Instead of having 1 billion rectangles, I should have infinitely many rectangles. So this means that I have to calculate the sum. I could write something like this. Yes? But this is not a good way to write it. Instead of writing, because infinity is not a number, so the mathematician doesn't treat it as a number. Whenever they want to work with infinity, they write it for n and then they take the limit and send n to infinity. But that's more or less the same thing. Yes? So I want to make sure that everyone I want to understand that this formula is a reasonable number for associating to the area for this area. Yes, to this what I wanted to talk. Yes?
What does K mean again?
K is just a counter I bring in. You can bring I, you can bring anything. K is this
At
counter.
the starting point, right?
Yes, not the starting point, the counter that tells you where to start and where end.
Okay.
So this tells you that the counter starts from 1, continues to n. So if you don't like K, you can choose I, you can choose J. That serves the same thing, yes? So the point is that, the take-home lesson is that, if I can find a way to calculate this, then the number that I get is a reasonable number to associate with the area that I want to calculate. Yes? Is that understandable? Yes or no? Okay. But the point is that how can I calculate the limit? So this up to this part is in the book, but the rest is not in the book. I want you to see this calculation. It is at the level of your math knowledge. It is not beyond that. But I think it would be fun if we can do that calculation. Okay, so let us just do this calculation once, because then I immediately tell you what Newton realized to get rid of all these heavy calculations with some genius, yes? Okay, so what we have to do. Okay, can you help me to do that? Let me write the formula. The function is, don't get confused, the function is what? X squared. And then I want to calculate what I need here is this part. Okay, can you tell me what is f of k over n? What is f of k over n? What is that?
K squared over n
N squared. So I replace x with k over n. So this becomes k over n squared. But it's better to write it as k squared over n squared. So let me start. A is the limit of sigma k goes from 1 to n, f of k over n times 1 over n, and n goes to infinity. So let me replace everything that I have. So this becomes the limit sigma k goes from 1 to n, and then I have what? F of k, sorry. Instead of f of k of n, I put k squared over n squared, and multiplied by an extra 1 over n. Yes? And then what happens? N goes to infinity. And then what I do, I multiply this by that, so this becomes the limit of sigma k squared, but divided by n cubed. K goes from 1 to n, but n is supposed to go to infinity at the end. Okay. Okay, so this seems that we are stuck, yes? Because we have to calculate this sum, but we don't have any formula for that. I just want you to feel what are the practical obstacles in front of you if you want to use this crude model, yes? And then you will appreciate the work of Newton much more, yes? Okay, so my suggestion for you is to expand this sigma, because still sigma is not a good thing for you to work with. You are better to get rid of this sigma notation. So what should I do? I replace k with 1, and then with 2, and then with up to n, and then add the terms, yes? So that's easier for you probably. So this becomes the limit, n goes to infinity. I replace k with 1, so it becomes 1 squared. I intentionally write 1 squared, even though that's 1, over n3. I replace k with 2, over n3. I replace k with 3. And I continue until I reach to the final point. So I will replace k with n. It becomes n squared over n cubed. Of course, you can simplify n squared when n cubed, but I intentionally don't simplify. So this is a little bit horrible limit that I have to calculate. Okay. So let me also talk a little bit about that. If I ask you, this is by the way at the level of your knowledge, if I forget about all the terms and I just concentrate here, and I ask you what is the limit of the first part, forget about everything coming after that. What is the answer?
0.
It is 0. Because it is a number divided by a huge, huge number, and if you remember we discussed about that, that becomes 0. So the limit of the first part is 0. What is the limit of the second part?
0.
0. What's the limit of the third part?
0.
0. And what's the limit of the last part? N squared will cancel 2 of them. N still is left in the denominator. What's the limit of the last one?
0.
0. And then you might say that, okay, I have a bunch of zeros and I'm adding them, it becomes 0. So the area is 0. Okay? So actually, which is nonsense, yes? So actually, this is the really, really powerful tool. Then this number 0 or not? This number is not 0, but its limit is 0. So what does it mean? It means that when n becomes extremely large, this number becomes smaller and smaller and smaller. But does this number become 0 at the end? No. So that was the difference between infinitesimal and 0, if you remember when I was talking. It's extremely important, even though I have... So that is the really powerful tool in your hand. Because if you add a bunch of zeros, no matter how many of them you have, the answer will be 0. But if you have a bunch of infinitesimals, little by little you add, then the answer will might not be 0. So as you see, it is not 0. So this number is not 0. The limit of that is 0. It means that when n becomes very large, this becomes infinitesimally small. So I have infinitesimally small, infinitesimally small. The point is that if I have a bunch of infinitesimally small numbers and I add them, it becomes, of course, infinitesimally small, unless I have infinitely many of them. Yes? So even though each part is extremely small, so say that I have 1,000 infinitesimally small numbers. Very, very, very small numbers. If you add them, it becomes still a very small number. But if I have infinitely many infinitesimals, there is no guarantee that the sum is still infinitesimal. And this is happening here. Can you see why? Because when I send n to infinity, of course I am increasing n, but I am also increasing the number of terms. Because I start from 1. If n is 10, how many terms are involved? 10 terms. If n is 1,000, each one of them is smaller, but I have 1,000 terms. Is that understandable? So when I make n 1 million, each one of them are really, really small, but on the other hand, I have 1 million of them. So even though I am making each part smaller, but I am increasing the number of infinitesimals that I am adding. So then, in this competition, who wins? It depends to our calculation. And then we have to calculate this. So I want you to feel the power of throwing 0 away and working with infinitesimal numbers. That's an extremely powerful tool, yes? That is the calculus. This is the arithmetic of infinitesimals, if you want. It's a little bit more complicated, but so powerful. Okay, first of all, I want you to understand this. And the other point is that how to calculate this limit. Because now you realize the problem is two-folded. Each time I am increasing n, I am making them smaller, but in the same time, I am making the number of infinitesimals more. So how can I calculate this? There is only one way to find a formula for this. If I can add this up, then probably I can hope that I can calculate this limit. Let me tell you something. Let me just go one step further. This one, because the denominators fortunately are all the same, so I can write it more compactly by putting just one entry in the denominator and write the 1 squared, 2 squared, 3 squared, up to n squared. So first of all, tell me, are you happy with what I have written right now? This one is exactly equal to this one because the denominators are the same. Okay, so it means that I have to find a way to answer this question. I don't know how many of you know that, but this is a very famous formula in mathematics, 1 plus 2 plus 3 plus n. Have you seen this formula before in Math 1C? Yes. That is arithmetic progression. So if I ask you, can you give me a formula for adding numbers from 1 up to n, I don't know how many of you remember, that is the formula. Yes? So, for example, if I tell you add 1, 2, 3, 4, and 5, of course, this is so simple that you don't need the formula because 1 plus 2, 3, 6, 10, 15. But if you put 5 in the formula, 5 times 6 divided by 2 is also 15. Yes? So that's a formula. By the way, this is called a closed formula for this sum. What do I mean? I mean a formula which is equal to this without these dots. That's a closed formula. Okay? The point is that, unfortunately, this is not very friendly. It's very similar to that, but I have second powers. Yes? So the question is that, can I find a formula for this? Okay, so this is the question that we want probably to answer here. So can we find the sum of this number? First of all, can I use arithmetic progression formulas for this one? Do you remember what was arithmetic progression? A sequence in which each term is obtained from the previous term by adding a constant number. So and that constant number is called the common difference. So 1 goes to 2 by adding 1. 2 goes to 3 exactly by adding 1. 3 goes to 4 exactly by 1. But here this is 1, this is 4, this is 9, the next one is 16. So you see that 1, 4, 9, 16. They are not arithmetic progressions. So I cannot use the formula. So that's the hard part. Yes.
But can't you use like the next term that comes and subtract it by the previous term?
Yeah. Somehow that's the trick. Exactly. So at least what I want you to see is that. What is happening is that we don't have arithmetic progression. So if we can solve this problem, we should be able to answer this question: that what is this sum equal to? Yes. And the trick we can use is actually what you said. I want to write it foremost. That the idea is correct, but what we just do is this. Let me see. So you start from this expression. So I would say k to the k plus k to the 3 minus k minus 1 to the 3. Yes, you might say why. I mean that you have to be really creative and smart to be able to find these indirect approaches. Okay, so let us first calculate this one, and then let me see how this will help me. Yes. So by the way, I just want to write some formula. There is a formula on the formula sheet that usually you don't use it, but that is this formula: a to the 3 plus 3a squared b plus 3ab squared plus b cubed. Yes? And how we can prove it? Very simple. You just write it as a plus b squared, a plus b, and use the squaring rule here, and multiply and simplify, you get immediately this. Yes? Let us change a to k and change b to minus 1, because I want to calculate this part. So then what happens? K minus 1 to power 3 becomes k to the power of 3 plus 3k squared times b, but b is minus 1. So let me just clean it and put it minus 1. The next one is 3a, which is 3k, but multiplied by b squared. B is negative 1. But when I square it, it becomes 1. And 1 multiplied by 3k is 3k. And then b cubed is minus 1. This is the expression. Yes? So I put it here. So this becomes k to the power of 3 minus this expression. So you don't have any clue why Babak is doing this, but I can guarantee that I am not in the mad mood, yes? So this should be done. But I just want you to feel what are really obstacles in front of you if you just want to calculate this simple area by that idea. Okay, let me simplify this. What happens? So you really don't need to be worried about learning these things so that you can reproduce them. Of course, if you are so interested in mathematics, there is no problem with that, but you need to sit and just enjoy the movie, okay? So this becomes done. And then what is left is this guy. K to the power of 3 minus k minus to the power of 3 is equal to 3k squared minus 3k plus 1. Yes? Okay, so don't forget about the main question. The main question is that I want to answer this. I know that, okay? So what we do, we go back to the other board because we need a lot of space. So let us calculate something. And by the way, that's also very interesting. That is what I'm saying. Archimedes was able to somehow calculate these kinds of sums without algebra, using geometry. That's extremely nice. If we can Google his method to calculate similar sums. I am doing a lot of algebra here, because algebra is more advanced these days. But he was able to construct a geometrical construct in his head to be able to answer that sum. Okay? So you see, he was really genius. So let us just calculate, see what happens. So I got a formula. I write it here in front of you. That formula up there. I realize that k to the power of 3 minus k minus 1 to power 3 is equal to 3k squared minus 3k plus 1. Yes? But now the interesting things comes in right now, okay? So what I do, write this and choose k equals to 1, because this formula is valid for whatever you choose for k, choose k equals to 1. Then what happens? It becomes 1 to the power of 3. Yes, 1 to the power of 3 minus 0 to the power of 3 is equal to 3 times 1 to the power of 2. I intentionally do not calculate, by the way. I'm just replacing k with 1. Do you agree? Now I replace k with 2. Then what happens? I think we are in trouble now. No,
Why?
I made a mistake. You know why?
Why?
It was not that hard. So forget about that. Let me do this. It was easier than I thought. K squared minus k minus 1 squared. I want to simplify that for you. No. That's correct. I'm confused a little bit. So let me think a little bit.
Take your time.
So 3k squared minus 3k plus 1. Yes. So if I go in this way, yeah, that's correct, sorry. So k1 is 1 to the power of 3 minus 0 to the power 3 is 3 1 squared minus 3 times 1 plus 1. And put k equals to 2. Yes, that was my mistake. 2 to the power of 3 minus 1 to the power of 3 is 3 times 2 to the power 2 minus 3 times 2 plus 1. And let me put one more for you. You can realize what the pattern is. K equals to 3. I put it here. 3 to the power of 3 minus 2 to the power of 3 is equal to 3 times 3 to the power of 2 minus 3 times 3 plus 1. Yes? And now, let us continue this method until I reach to the very end. K equals to n. Then what happens? This becomes n to the power of 3 minus n minus 1 to the power of 3 is equal to 3 times n squared minus 3 times n plus 1. Yes or no?
Yes.
I generated the formula for you. That's the proof. I am using it over and over again by replacing k with different values. But because of pedagogical reasons, I think it is instructive. When you end up at n, it is clear what is the previous step.
N minus 1.
N minus 1. So when I replace k, let me write that one. That's for pedagogical reasons. Agree? Yes? Everyone agrees?
Yes.
Now, the miracle happens here. When I add them up, this hard part mainly cancels out. How? This is called a telescopic sum. It's like a telescope that you press them, it will go on. So you see what happens. Let me add them up. The left-hand side, which is the hard part with the third powers, are more or less cancel everything. So what's happening? 0 is just 0, forget about it. It's already cancelled out. Yes? But now this one and this one is negative, so they are cancelled. And then when I go to the next step, there is a negative one here, which will cancel that one. And then when I go to the next step, one thing coming here will cancel that one. And if you continue in this way, you see this one will be cancelled with this one, this will cancel with the previous one, and what is left is just this one. Yes? So when I start adding them up, there is only one term that survives, and that is n to the power of 3. Yes? But on the right-hand side, when I start adding them up, I intentionally wrote it in this way, because you see I have a 3, a 3, a 3 up to n. I can factor a 3 out. From the first one, 1 squared is left. From the second one, 2 squared is left. From the third one, 3 squared is left. And this will continue. The last one, n squared is left. Yes? And then I will have the middle terms. I have minus 3, minus 3, minus 3, minus 3, minus 3. I can factor a minus 3 out. the first term, positive 1 is left. From the second term, positive 2 is left. From the third term, positive 3. And then the last term, positive n. Yes? And then I have 1 here, 1 here, 1 here, 1 here, 1 here. I start adding them up. How many 1s I have? How many 1s?
Infinity.
No, infinite, no.
N.
N. Because 1, 2, 3, 4, up to n. I have n. So it becomes n. Yes or no?
Yes.
So this is the sum. This is my question mark, by the way. Do you agree? This is my question mark. But what is this one? Arithmetic progression. It's n times n plus 1 divided by 2. So I am done. I am looking for my question mark. I have to make my question mark alone. So what I do, I move this one and that one to the other side and then divide everything by 3 to get my question mark. Yes? So, let me just do this calculation. So, n to the power of 3 is equal to 3 times, if you don't mind, let me write question mark, minus 3 over 2 n times n plus 1 plus n. Yes? And then I am looking for my question mark. So I move these two to the other side. So it becomes n to the power of 3 plus 3n times n plus 1 divided by 2 minus n is equal to 3 times my question mark. I would prefer to simplify this a little bit. So I take the common denominator 2. I multiply it here, this becomes 2n cubed plus 3n times n plus 1 minus 2n is equal to 3 question mark. And there is an n, and n. I can factor it out. 2n squared. I factor an n out, 3 and n plus 1 is left. I multiply in. So it becomes 3n plus 3. I have minus 2n here. And then I have divided by 2 is equal to 3 times question mark. And then you have n. You have 2n squared. 3n minus 2n is how much? Is plus n plus 3. And then divide by 3 because you want to make question mark alone. If you divide this by 3, the denominator instead of 2 becomes 6. Is your question mark. Yes? And we can even write it better. So the question mark is n plus 1 times 2n plus 1 and divided by 6. Why is that? Because take your time to multiply. N times 2n is 2n squared. Yes?
But before you factor out minus 2, and shouldn't just be minus 2?
Yeah, I have a small mistake somewhere because this formula is in my head. What I get is I miss something here. What is that? What you mentioned?
Like you factor out n,
Here.
you're minus 2 and...
Yes, this is minus 2, thank you. Thank you very much, that was my error. Thank you. So this is 3n, because I realized I have it in my head, that's it. And then what is this one? This is 1. Yes, that's correct, thank you. Thank you very much. Thank you. Okay, so now test this, is that right? Because n times 2n is 2n squared. N times 1 is n. 1 times 2n is 2n. 2n and n becomes 3n. 1 and 1. So that's completely correct. So we were able to rediscover this formula. So by the way, the person who discovered this formula is also brilliant to start with something completely probably irrelevant and be able to understand if they do something like this, what they will get at the end is what they want. Yes? So you have to be very creative. So that is the formula that I can put instead of this question mark there. This question mark is now known to us. Yes? I hope that you haven't forgotten the problem. The problem is here. Yes? We go back. By the way, I hope that you see the person who actually first wrote this solution, he was extremely creative to be able to start with such a scenario. If you want to be creative, calculate this, by the way, for third powers. Calculate this for third powers, the same trick will work. But you need to be creative again. Exactly the same trick. Be able to calculate 1 to power 3, 2 power 3, 3 to power 3, and to power 3. Yes.
Could you move the lower board a bit down?
Yes, I will do. I have to move it a little bit up. And then this one down.
Thank you.
Okay. Now, I hope that you haven't forgotten the main problem. We go back here and then try to put the formula we rediscovered here. So n to the power of 3 is in the denominator. Instead of this one, I put that expression that I got on top. N times n plus 1 times 2n plus 1, but divided by what? 6. N goes to infinity. By the way, every bit you were able to follow. So this means that you already knew a lot of mathematics. Because everything that I wrote on the board, it is understandable for you. Yes? So you need to be proud of yourself. You have a lot of math knowledge now. Okay, so what we do, this n and one of these n's are cancelled. So this becomes the limit. One of these n's and one of these n's are cancelled. So I have n plus 1, and I have 2n plus 1. And by the way, this 6 goes down, 6n squared, yes? And n goes to infinity. But that is exactly at the level of your math lesson to calculate this, and we had it in chapter 1. I want you to see how many of you remember. So let me multiply this, 2n squared, and then I have 3n if I simplify, and then I have 1 divided by 6n squared. Do you remember how we calculate such limits in chapter 1? But of course, in chapter 1, instead of n, we had x. But that's the same story. Do you remember how we calculate this? From chapter 1. Yes?
We did it to get n as the denominator, so we could.
Yeah, so we divide by the highest power of n, x squared. See here, I divide everything by n squared. 2n squared divided by n squared becomes 2. 3n divided by n squared becomes 3 over n. And then 1 over n squared. So that's important. If you start forgetting about things that you have already done, then of course every bit of this problem is completely new problem, and then you will not be able to solve it, even if you are super genius. Okay? So then what happens? N goes to infinity. But what was the reason we did this? Because if I ask you what is the limit of 3 over n, you can answer. What is that? When n goes to infinity? 0. And then that's also 0. So what do I get? I get 2 over 6. Yes? And the answer is 1/3. So all what we have done even is just we have done it for 1/3. So the area, exact area of that I started is 1/3. And then I hope that you appreciate there were very real problems in the way. What was the main problem? The main problem, can you just tell me which part of this was the main problem? So I had done a lot of calculations.
Yes.
So more or less, you see, we came up to here immediately. So this is exactly where I started, and I had up to here. So it is under 1 minute probably, we did this part. But the whole thing that I have done, I was quite busy to calculate this sum. So I would say that the hard part of calculating was calculating a formula for this sum. Is that clear? So remember this. But now let us see what Newton realized. Newton realized that, okay, don't do these things. Find a primitive function for x squared. What is a primitive? So totally unrelated. God, this is area, that's primitive function, but do it. What's the primitive function for x squared? This is why I ask you to repeat a little bit. What is a primitive function for x squared? The simplest ever possible function, yes?
1 over 3x to the power.
Yeah, x to the power of 3 over 3. So what was the area you are interested in? Is between which numbers? 0 and 1. Newton realized put 1 here, becomes a third. Put 0 here, it becomes 0, and subtract them. That's your number. This is Newton's method. Yes? So he realized that instead of doing this mess, you can ask yourself, what is a primitive function for your function? If you can answer this question, just put these numbers into your function and subtract them. The answer you get is the final number.
So easy.
Yeah, so easy. Yes? Yes.
So Babak, are you saying that all of this calculation was for nothing if we could just...
Yeah, exactly. That's not for nothing. That is, I want to say Amen. How do you say it? I don't know. Salavat befresin be ruh Newton in Persian, but in English I don't know how to say it. So you need to respect Newton. Yes, and of course many people believe that also Leibniz discovered that independently. Leibniz was actually a genius German mathematician, and of course, apparently they were not good with each other at that time. But Leibniz was also a great mathematician, philosopher, and even computer scientist, I think. But it's very interesting, by the way. Check, I forgot the name of the machine. He actually not only invented, I think he also manufactured to calculate the sum of the numbers or something mechanically. I will try to find it out. So, I mean, let us just try and go back and digest what is happening here. So, what is happening here is the idea works, but it's extremely hard. By the way, this is probably one of the simplest possible functions in mathematics. Now just think what will happen. For example, if I change this to a square root of x, then what will happen here will be a sum involved with the square root of 1, square root of 2, square root of n. Then I will not be optimistic even to find this sum. So I will answer you. So this means that Newton not only solved the problem easier, but he was able to solve the problems that we were not able to solve in this way. Because if I started with the square root of x, you will end up with the sum of this form, and there is no way to find this sum in a closed form. But if I give you this function, immediately you can find the primitive function. You write it as x to the power of 1/2, and the primitive function is what? 2/3 x to the power of 3/2. And then I can do the same thing more or less immediately. Yes? So you see that it not only gave a simpler way to do the problems that we can do, but he also gave the solution to the problems that we cannot do like this. Yes, and I will talk about the Newton's method, how he probably, it was not that hard, but of course, if the problem is solved, you can always say that, okay, it was not that hard, yes. Yes?
Which part was the calculation for Newton's method?
This one.
Only this.
So, no, 1/3 minus 0, which of course is 1.
And where did you get those numbers from?
Those numbers is 0 to 1. That was the area that I was interested
Okay, you took the primitive function of the function, and then you put in the
endpoints
endpoints.
and subtract them.
Okay.
So that's the Newton method, yes? Okay, so I will actually stop here. None of these things you need to learn. Even though everything that I talked was exactly at the right level with the knowledge of math that you have. Okay? But I want you to understand today, so the take-home lesson is this. This formula is reasonable. Yes? If you don't have any objections, then we don't have any fights. Yes? The only thing that I want you to learn from all these calculations is that this formula is reasonable. Yes, for the area. That's it. Any questions? Goodbye.
So we're gonna do this